25 degrees centigrade. So we write it as concentration of H plus is equal to concentration of OH minus, that is approximately equal to 1 into 10 to the power minus 7. So if we take the log of both the sides of concentration of H plus and the concentration of OH minus, that is, it becomes minus log of Kw is equal to minus log of H plus minus log of OH minus. So as a whole, the equation is given as pKw is equal to pH plus POH. So from this equilibrium, the equation that I have highlighted, it is clear that the pH scale, it lies between 0 to 4. Sorry, 0 to 14. So in most cases, we come across the pH of the solution ranging from 0 to 14. When we talk about the pH of normal water, it lies in the range of 7. That indicates that it is neutral in nature. A pH that is below 7 indicates the acidic nature of the solution, and the pH above the value of 7 and up to 14, it indicates the alkaline nature of the solution that we have taken. So the pH measurement is an important property in electroanalytical chemistry, and it is usually measured with the help of a glass electrode and a pH meter. So the pH meter is one of the most commonly used methods, or it is the most common methods, the equipments for measurement of pH. Nowadays we have digitalized pH meter that just directly displays the pH of the solution into the displayer. So however, we also use the glass electrode, and it has also very good accuracy and precision. So we'll first start with glass electrode and then we'll move on to the use of pH meter. Now the glass membrane electrode, or the which is called as the glass electrode, it is a very common example of an ion selective electrode. So it indicates that this electrode is very sensitive to the nature of the ion that is present in the solution. So the overall cell, when the glass electrode is used with an external reference electrode, that is mostly a calomel electrode, or we say it as a saturated calomel electrode, SCE, is represented by the following formula: glass membrane, single bar, H plus, the salt bridge, and the SCE, that is the saturated calomel electrode. Now when we take the cell potential, we write it as the total cell potential E cell is equal to the EMF of the SCE plus the EJ, that is the EMF of the liquid junction potential, EG0, that is the standard electrode potential of the glass electrode that we have taken, and minus 0.059 into log of H plus, concentration of H plus, that we need to compute. So if we arrange this equation, we can write it as E cell, the EMF of the cell, is equal to E star plus 0.059 log H plus. We have rearranged this log H plus to pH, and the sign is also changed here. Here the the E star, which has been represented here, it indicates the E star, it indicates the potential of the glass electrode, the liquid junction potentials, and other the constants that is present inside the solution. So from the equation 3.1, we can find out that E cell is directly proportional to pH. So this is a very important factor. Now we will focus on this E star. This E star, as we have said, includes Sir, may I continue?
ନା ଏଇଟା ଆମେ ଦୁଇଟା ମୁଁ ଏବେ ଡିଜାଇନ୍ କରିଛି ଏଇଟା କ୍ଲାସରୁମ୍ରେ ଦୁଇଟା ଏଥିରେ ଶୁଭୁଛି ସେଇଟା ସ୍ପିକର ନାହିଁ ଏଇଟା ଏବେ 11ଟା ବେଳୁ ଆରମ୍ଭ ହେଲା ଗୋଟେ ବେଳେ ସରିବ।
Okay. So we were talking about E cell is directly proportional to pH of the solution. Now we will specifically focus on E star. This E star, it includes the standard potential of the glass electrode, the reference electrode. It also includes the liquid junction potential and other factors that is present in the solution. Besides all this potential, there is another potential which is called as the asymmetric potential, and it also contributes to the value of E star. Now, asymmetric potential is a small potential that exists within the cell even when the reference solution and test solution are identical in nature. However, the origin of this asymmetric potential is not yet very much clearly understood. It has mostly been due to people have mostly found out that this might be due to the degree of hydration of the inner surface and the outer surface of the glass electrode, or due to some manufacturing defects. Even when the both the inner and outer solution remains the same, that is the test solution, the indicator solution and the reference solution remains the same, there arises a very minute value of asymmetric potential. So the degree of hydration of the outer surface is also changed when the electrode is dry out. Because of this, it has been because of the presence of this asymmetric potential, it is always advised that the electrode should be stored either in water or in damp cotton wool. Mostly in laboratories, what we do is we cover the tip of the electrode in some water in a water, and it is kept away from the source of water. So it is not possible to determine the value of the asymmetric potential. So because it is present in very minute quantity, the measurement of asymmetric potential is very challenging. That is why we need to calibrate the glass electrode with suitable buffer solutions. So whenever we go for the measurement of pH metric, the first thing that needs to be done with a pH meter lies in its calibrations, and the calibration of a pH meter is usually done with different buffer solutions. In general, we have three buffer solutions of pH 4, 9 and 7 that are used for the calibrations of the pH meter that we will discuss later. So, asymmetric potential, although the value is very less, it contributes significantly to the E star value, and thus we need to be very cautious while calibrating the pH meter before our actual experiment. So now we will, in brief, we will talk about the glass membrane electrodes. So first we will talk about glass membrane electrodes, then we will go for the pH meters. In a glass membrane electrode, the glass electrode is very fragile. As you know, glass is, as it is, very fragile in nature, and also in glass membrane electrodes, the glass is made up of silicates and it is also very fragile in nature. The glass membranes, these glass membrane electrodes, they are mostly ion sensitive electrodes. That is, they are particularly responsive to one type of ions only, and they remain unresponsive to the other ions. That is why they have mostly been shortly called as ISE, that is ion selective electrodes. Now the glass membrane electrode, a diagram has been presented here. In figure 3a, you can see this is a typical glass electrode which consists of a glass electrode and a reference electrode. And in the B, it shows how the ion exchange occurs within the glass electrode. So in a glass electrode, these electrodes are actually made up of thin glass membranes. The main body of the electrode, it contains an internal reference that is typically, in most of the cases, a silver chloride is used, and it is filled with the solution that is mostly HCl of concentration 1 molar. The selectivity coefficient of the glass membrane is such that it has excellent dissemination against most of the cationic species. That is why glass has been used and HCl of 1 molar is used. The pH electrode, it responds to the hydrogen ions as a result of the thin ion exchange sites on the surface of the glass membrane. Now, as you can see in figure 3.1b, it shows the interface between the internal glass electrode and the outer glass electrode, which acts as the surface of exchange of ions between the glass and the solution that is present inside. The electrode consists of a thin layer of glass, mostly a very thin layer of 50 micrometers, that is 50 into 10 to the power minus 6 meters is taken. The charge is transported across the membrane by the sodium or the lithium ions that is present in the glass. Since glass is typically made up of sodium silicate, so here the ion exchange of okay. So when the boundary potential is developed between the difference between, so a boundary potential is developed between the surface of the glass, which we call it as and refer it as EB. So the chemical reaction equation for both the boundary potentials can be written as H plus into glass minus. This is for the outer surface of the glass, which gives H plus the glass minus, whereas in the inner surface of the glass, that's also a potential difference giving rise to H plus and the glass minus equation. So combining both these equations, we can write E1 is directly proportional to A1 minus AH, whereas A1, it represents the activity of the hydrogen ions in the test solution, and AH represents the activity of the hydrated layer. Similarly, from equation 3.4, we can write E2 is directly the boundary potential for the outer hydrated layer can be represented as E2 is directly proportional to A2 minus AH. So combining both this equation, we have an overall boundary potential, that is EB, which is equal to E1 minus E2, that is directly proportional to A1 minus AH minus A2 minus AH. So if we assume that both the activity of the H plus ions in the inner and the outer layers are the same, then we can neglect the AH from both the cases, and we can write EB is directly proportional to A1 minus A2. So, but the activity of the hydrogen ions that is present in the inner solution, it remains constant, and that is why the above equation reduces to EB is directly proportional to A1. Now, overall, if we try to express the boundary potential in the form of Nernst equation, we can write it as EB is equal to E1 minus E2, which is equal to 0.0591 into log of activity of 1 by A2. So, where this is further rearranged to form EB is equal to K1 minus 0.0591 into pH. So here the K1 is a constant which it relates to the hydrogen ion activity in the inside solution of the glass electrode, and 0.0591 is a value from Nernst equation, and this is the pH. So thus from equation 3.5 we can say that boundary potential is a direct measurement of the pH of the external solution. So this equation is very important, that is EB is equal to K1 minus 0.0591 pH. So from this equation we can know, it has been inferred that the pH is directly, the boundary potential also influences the pH of a solution to a great extent. Now when we measure the pH with a glass electrode, a very common setup is made, and this has been shown in figure 3.2. This is a very common setup for measuring the pH of a solution using a glass electrode. In this arrangement, AgAgCl reference electrode is taken, and the external electrode such as SC is also taken. So here, and the overall reaction, the overall arrangement is represented like this. So this process is very easy, and the measurement is also quite accurate and proceeds flawlessly. The cell potential of the overall system is given as E cell is equal to E ind minus ESCE plus EJ. So here ESCE represents the EMF of the standard calomel electrode. E cell represents the total cell potential, and EJ represents the potential of the liquid junction potential, and EIND is the potential of the glass electrode. Now, when we combine the above equation and put it in terms of EB, we find out that the indicator electrode is actually a combination of three components, that is the potential, the boundary potential EB, the potential of the reference electrode, that is AgCl, and the asymmetric potential, which plays an important factor in the determination of the overall potential, and we write it as EASY. So therefore, considering all the three contributions of the indicator electrode and putting all these values in equation 3.6, we find that E cell is a combination of EB plus E of AgCl plus E of asymmetric potential minus the potential of the standard calomel electrode plus EJ, that is the potential of the liquid junction. So substituting everything, and finally the value of EB in this equation, we find that E cell is equal to E star minus 0.0591 pH. So here E star is a constant which includes the potential of the reference electrode, the liquid junction potential, the asymmetric potential, the boundary potential. It has all been included in this E star. Now, the determination of E star is actually very challenging both experimentally and theoretically, and hence we have, as we have already discussed, the calibration method is generally used to eliminate this E star factor. So in the first method, the test solution comprises of a standard buffer solution. A buffer solution is one solution whose pH we have known already. So thus for the standard, we can write the following expression, that is E cell of the standard solution is equal to E star minus 0.0592 of pH of the standard solution. Then this step is followed by the measurement of the cell potential for the unknown solution. Similarly, for the unknown solution, we can also write it as the E cell of the unknown solution, which is given by U, is equal to E star minus 0.0592 pH of the U. So here U represents the unknown solution. Now to eliminate the E star from both the equations 3.9 and 3.10, we subtract it, and then it has been found that pH of U, that is the pH of the unknown solution, is equal to the pH of the standard solution minus the EMF of the unknown solution minus the E cell of the standard solution divided by 0.0591. So this equation, the equation 3.11, it has been adopted throughout the world. It has been accepted globally as the operational definition of pH. So that is why the overall, when we look into the pH, it takes this equation into account and displays the pH value of the unknown solution. The pH determination using glass electrode is most accurate, and it is widely used method, but it also has a few disadvantages to its credit. The first one being the glass membrane is very fragile in nature, and it requires great care while using. As we have already read, the glass membrane thickness is 50 microns in nature, that is 50 micrometers, so it is much fragile and it needs handling with utmost care. The ordinary potentiometer cannot be used for measuring the potential of a glass electrode. Thus, electronic potentiometers are required and they need frequent standardization and cannot be employed in pure ethanol, acetic acid, and other medium. So that is why the following features of glass electrode have made it more versatile to be used as a indicator electrode for pH measurement. That is why, because of these certain disadvantages, we have the following features of the glass electrodes were introduced. That is, it may be used in the presence of a strong oxidizing and reducing solutions in viscous media, and in presence of proteins which interfere with the operation of other electrodes. It can be used for solutions having pH values 2 to 10, but some special glasses needed. Measurements, they can be extended to pH values greater than 10. However, for this we need normal glass electrodes. Although normal glass electrodes have been employed for the measurement of pH values greater than 10, we do find some complications and some anomalies in the reported values. So that is why it is always advisable to use a specialized glass for measurement of pH values greater than 10. Now, however, it is simple to operate, and it is the glass electrode is totally immune to poisoning, and here the equilibrium is reached quickly. So, while measuring pH, we should always be little careful, as there are few factors which limit the accuracy of pH measurements. Although the working principle of this glass electrode is very easy and the handling is easy, there are certain errors which need to be taken care of during the measurement of pH. The first one is termed as alkaline error. It is noticed that this error particularly arises when the ordinary glass electrode, it becomes sensitive to alkali ions, and they give low reading in the pH range above 9 or 10 units. Now, in general, a glass electrode has been used because that is particularly called as ion sensitive electrode, because they remain inert to some the ions. However, an alkaline error, it arises when those glass electrodes, they become sensitive to alkali ions. The reason for this error is that while the glass membrane is selective to hydrogen ion, it sometimes responds to other ions. This becomes more significant when the activity of the other ions is comparatively much higher to the activity of the H plus ion. So thus, this error arises, and this error is called as alkaline error. And particularly when we look into the graph 3.3, we see the alkaline error is relatively more in case of sodium ion, and this is because the higher selective coefficient of sodium ion, because sodium ion can be reduced by the use of Li2O glass in place of Na2O glass. Now, with more sophisticated glass electrodes coming into the market, previously sodium oxide Na2O was predominantly used. However, due to the presence of this alkaline error, today's world, we have come across a sophisticated glass electrode, and that has been made by Li2O, which have replaced Na2O glass. Okay. The second error, while working with a pH glass electrode, that needs to be taken care of is the acid error. The here in this error, at low pH range, that is less than zero point 0.5, the values determined by the glass electrode, they tend to be much higher than the actual value. This error is particularly due to the activity of water, which we have ignored while considering the Nernst equation. While deriving the Nernst equation, we have considered the activity of water as 1. Now, whereas in solutions, in a highly acidic solution, the activity of the water becomes less than unity, and because we have more number of protons hydrating the solution. So, and as a result, an error arises which is termed as the acid error. So, because of this, the net result will be that the pH for the solution will be very, very high. So these are the two major errors that can arise while working with a glass electrode. A third type of error arises, that is called due to the variation in junction potential. In most of the cases, what we see, the composition of the standard buffer solution and the test solution are different. So as a result of this, the liquid junction potential is different, and this is also one type of error which which shows a wrong value of our instrument, of our solution. Now, error in the pH of the standard buffer. There may be a possibility that the buffer solution that has been used for the calibration of the instrument is not prepared with proper care, and thus its composition might have changed during the storage period or any other factors. All these factors will cause a subsequent error in the pH measurement. So the preparation of the standard buffer is also a important factor that needs to be considered. Now, temperature is also one factor that can lead to error in pH measurement. A change in temperature, it affects the pH measurements, because the change in temperature, it affects the activity of the ion and also that of the liquid junction potentials. That is why, to totally remove the possibility of the temperature changes errors that might occur in the pH instrument, it is advised that the instrument should be properly calibrated. Now, the calibration process also sometimes leads to error, and this is mostly caused when the buffer solution has not been prepared more accurately than 0 plus minus 0.01 pH units. Therefore, we cannot calibrate the electrode properly. Once the calibration is wrong, then the total measurement becomes wrong. And there is also an error which might be equipmental related, that might be due to power fluctuations, parallax errors, the scales, and etc. So these are the certain precautions that we need to take care while measuring the pH in a gas electrode. Okay. So after the glass electrode, we have the pH of a solution can be measured from an instrument that is called as pH meter. The instrumentation that is required to perform potentiometric measurements, that includes a reference electrode, an indicator electrode, and a high input impedance electrode that we have seen. Now, ordinary lab voltmeters, they cannot be used for the measurement of the EMF of a cell. When we have an ordinary instrument, it is not at all possible to measure the total EMF of glass electrodes, because it is highly resistant to glass electrode. So the pH meter in general, it is a voltmeter, but it has some additional features, like not only it measures the potential across the pH sensing reference electrode, but it also converts the potential difference measurement at a given temperature into pH terms. The overall function of the pH meter is quite similar to that of a voltmeter, but it overall converts the whole mechanisms and gives us the pH value as a total output of the system. The operational controls on a pH meter are best understood while we consider the operational manual provided by the manufacturer of individual instruments. So while handling a pH meter, it is always advisable that we follow the manual and the instructions provided by the manufacturer, because the working principle remains the same, but the use varies from company to company. Modern electrode techniques permit the production of a simplified pH meter that measures with an accuracy of plus zero point 0.1 pH unit. The sensor, the microprocessor equipped pH meters, they include a temperature probe that also display temperatures, a memory for the pH values, and other electrodes. Along with pH meter, we also required a reference electrode and a glass membrane electrode, which act as an indicator electrode in pH measurement. So what is a reference electrode? And we know the two most popular types of reference electrodes are the SCE, that is the saturated calomel electrode, and the silver chloride system electrode. Both are reference electrodes, and they have some ideal characteristics, and the primary being that their potential remains fixed over time. They do not show any change in potential with time and temperature. They have long term stability, and they return to their initial potential after being subjected to variations in small current. So, that is why, in most of the cases, the reference electrode has been chosen as the SCE or the silver chloride electrode. The SCE is composed of a metallic mercury solid HgCl2 and a saturated KCl solution at equilibrium. So the potential of SCE remains constant even if some of the liquid evaporates over time. This the SC is also quite popular with a constant temperature bath, and the error can be eliminated. The minute errors arising during the experimental, that can be neglected. The SC can be used as a reference electrode in a sample that does not exceed 80 degrees centigrade. So this is one of the most commonly used electrodes in laboratories. The silver chloride electrode, it includes a silver wire which is coated on one end with a silver chloride salt that is insoluble. When the electrode is immersed in saturated KCl solution, its potential depends only on Cl minus concentration versus the standard electrodes, standard hydrogen electrode. The silver chloride electrode, it should not be used on solutions that contain species which can precipitate with silver, like that should not be used in solutions containing sulfate or carbonate where the complexes can precipitate with silver. So such complex compounds are avoided. So the reference electrode should be prepared and the maintained so the level of the internal liquid is kept above the sample to avoid infusion of the sample into the reference electrode. This is a commonly used precautionary method to avoid any contamination of the sample by Cl minus, Ag plus or Ag2 plus. In most general cases, we have seen that the reference electrode, either it is SCE or AgCl, they are maintained the level, they are mostly dipped in a solution of KCl so as to avoid any contamination of the sample by Cl minus or Ag plus in most of the cases. So now coming to the measurement of pH in a pH electrode. So by pH metry, pH measurements, they are routinely done and they are mostly, pH can be measured in many ways. However, only two methods are widely used, others being complicated. The one is the use of a colorimetric indicator methods, that is what we call as pH paper or pH strips. The secondly and the most demanding that has been used is the use of glass electrodes and pH meters. Now these, the colorimetric methods, that is the use of pH paper, is just a very basic method, and it relates just to an visual observation of the color of the solution with that or that seen in the pH paper. The and this method is not at all advisable, although just it gives an preliminary idea about the pH of the test solution. Mostly pH determination is done by potentiometric methods, and because it is free of interferences and it includes the use of glass electrodes and pH meters. So potentiometric method of pH measurement. The pH is determined by the measurement of the EMF of a cell, which consists of an indicator electrode, a reference electrode that is usually a standard calomel electrode or the silver chloride electrode, a liquid junction potential. The EMF of the cell is measured with pH. Now the discussion has already been made here. The discussion about the apparatus. A pH meter, it consists of a potentiometer, a glass electrode, a reference electrode, and a temperature compensating device. So a balanced circuit is first completed with the potentiometer. The reference electrode is a general SCE, that is standard calomel electrode or silver chloride electrode. The glass membrane electrode can be of very types. Even combination of glass and reference electrodes are also available. The beakers, mostly polyethylene beakers are used, and a magnetic stirrer is used for the mixing of the samples. Now, first thing, before the measurement of a or the pH of a unknown solution, the first thing that we all need to do is the calibration of the instrument. For the calibration, buffered tablets having pH of 4, 7, and 9, they are most commercially available and commonly available. So they are used. So for the preparation, even if they are not available in the market, we can prepare them, and the process is as follows. The pH 4 buffer solution is first prepared by dissolving 10.2 grams of anhydrous potassium biphthalate using a boiled and cooled distilled water. Then the second, pH For pH 7 buffer solution, we dissolve 1.361 grams of anhydrous potassium dihydrogen phosphate and 1.42 grams of anhydrous disodium hydrogen phosphate, both of which have been dried at 100 degrees centigrade. Then they were diluted with distilled water, boiled and cooled. So this gives us a buffer solution of pH 7. Now, to prepare a buffer solution of pH 9, 3.8 grams of borax is dissolved in distilled water and the volume is diluted to 1 liter. So, even if we do not have buffer tablets, they can be alternatively made in the laboratory with the help of these reagents. Now, once the instrument is calibrated with the buffer solutions, then the following procedure is adapted. These days we have digital pH meters. Now digital pH meters, they display the pH value of the solution and with a plus minus of 0.01 pH units. So and they are most popular and they have actually grown in popularity owing to their precision. The measurement of a pH of a solution can be made following the procedure. First, the selector, which we keep on to zero position and adjusting the zero position by the pointer that is provided. By using the pH meter, the electrodes from the storage, before using the electrodes are properly rinsed with distilled water and then they were dried with a soft tissue paper. The electrodes are then clamped onto the stand. Then the power supplied is supplied to the P instrument, and finally it is allowed for 5 minutes to warm up. The temperature is set to the room temperature. Then the standard buffer solution is taken and the instrument is calibrated. It should be seen that the glass electrode membrane is completely immersed in the solution, and then after selector is switched to the suitable pH, we adjust the pH according to the buffer that we have taken. Then the selector is switched back to after our instrument is calibrated with the pH of the buffer that we have taken. The selector is again switched back to zero. So these the electrodes are washed properly. Now what we do, after the electrode, only one buffer is sufficient to calibrate the instrument. However, we can also take the pH of other buffers and calibrate it. After we clean the glass electrode, then the it is dipped in the solution of unknown solution, and then the electrodes are the magnet is stirred gently in a magnetic stirrer, and then the pH is displayed in the front of the pH meter with a standard deviation of 0.01 pH units. So this is how the overall, from figure 3.4a we can see how the pH meter, it displays the pH value. So there are certain precautions that need to be taken. The first precaution is the pH membrane. The membrane of the glass electrode should not be touched with bare fingers because it is fragile and it could be scratched if we touch with bare fingers. The electrodes must not be removed from the solution. Okay, unless the pointer indicates to zero, the electrode must be dipped in the solution. Never dip the glass of the electrode with a dehydrating action. So a dehydrating solution, it scratches the glass electrode. For sample analysis, equilibrium between the electrodes and sample stirring must be ensured. If while we are measuring pH of a very albuminous substance, then the electrode must be cleaned properly since albumin sticks to the glass of the electrode. So the glass electrode must be cleaned with proper solvent, or else we will see error in the measurements of other samples. For basic solutions where the pH ranges more than 11, the glass electrodes of special composition need to be used so as to avoid the interference of the sodium ion, and for this purpose lithium oxide has been used. The glass electrode must be covered. It should always remain covered so as to prevent by the attack of moisture or other environmental factors. The standard buffer of pH value as close to the possible same pH value must be taken for the calibration system. Now, whatever buffer we have taken for calibration must be similar to that the pH value is displayed in the pH meter. So, calibration plays an important factor in the measurement of a pH. So, these are some of the precautions that we need to follow. Then coming to the concept of pH titration. Similar to as we have already seen, potentiometric titration. Similar to pH titration, potentiometric titration, pH titrations are very accurate, very precise, and the errors due to the liquid junction potential are minimized, and it is a very easy follow. It's an easy procedure to follow. So before going a typical acid-base titration pH metry, let us consider that uses that it actually indicates the neutralization accompanied by the changes in the concentration of H plus and OH minus ions. In most cases, hydrogen electrode may be employed in these titrations. The reference electrode that has been used in this acid-base pH metric titration is a 1 molar calomel electrode. This is the apparatus that is shown. That is a typical setup for a acid-base pH. This is a pH titration. So the critical problem, one of the in titration, is recognizing the point at which the quantity of the reacting species are present in equivalent amounts. That is the major indication of the equivalence point in this acid base titration is an important factor. The titration curve can be followed by plotting as a ordinate successive, or we can rightly draw a perpendicular to the x-axis and indicate the and know the equivalence point. So over most of the titration range, the pH it varies gradually, but when the endpoint is near, the pH changes very abruptly. So as a result, we can see the curve of the graph. This is a pH titration curve in figure 3.6a. So from this plot, when we see a drastic drop in the pH value and we draw a perpendicular, we ultimately from the value of the perpendicular drawn to the x-axis, we can know the equivalence point. So the end point can be located from the inflection point of the titration curve. This is the point that corresponds to the maximum rate of change of pH per unit volume of the titrant that is added. The equivalence point can be more precisely located from the first and second derivatives as shown in figure 3.6b and c. So when we plot the first derivative curve and the second derivative curve, we can see the equivalence point. Can it the precision or is very clear? The equivalence point is known very clearly. However, the solutions for particularly this pH metry is very efficient. However, but for more dilute solutions, that is for solutions greater than 10 to the power minus 3 molar, the pH metry does not hold good. Both pH metry and potentiometric titrations do not work in more dilute solutions. Now, considering different cases of pH metry, suppose we want to titrate a weak acid with a strong base. So, for the titration, as we can see in figure 3.6a, it is the titration of a strong base with a strong acid. Now, when we consider a weak base and a weak acid and a strong base, that is CH3 acetic acid and sodium hydroxide, the titration, the pH metric titration is occurs differently. Now, what happens is the starting point of the titration at the beginning, since the acetic acid is considerably lower than HCl, at the beginning of this, then HCl, the acetic acid dissociates very less in comparison to HCl. So what happens here is the more we can write the expression for dissociation constant for acetic acid as Ka is equal to concentration of H plus A minus by concentration of Ha. Now when at equilibrium the concentration of H plus is equal to the concentration of the anion, that is A minus or CH3COO minus. As the degree of ionization of acetic acid is very small, therefore the concentration of the unionized acid is almostly equal to the concentration of acid, that is H plus A minus is approximately equal to the concentration of the unionized acid. Therefore the dissociation constant Ka can be written as H plus whole square by concentration of C acid. So for particularly for acetic acid, we know that the Ka, that is the dissociation constant, is 1.75 into 10 to the power minus 5. So when we look into the pH, this is pH is minus log of H plus, and this comes to be 3.03. So the equivalence point for the pH of this solution of acetic acid and HCl is remains as 3.03. We can also determine the pH at the equivalence point at the moment when the titration completes. Equivalent quantities of CH3, COH and NaOH will be present. Hence, the titrating flask will have a salt solution formed by a weak acid and a strong base. Now we know that from the hydrolysis of salt, we know that H plus is equal to Kw into Ka by C of salt, where Kw represents the hydrolysis constant of water, Ka represents the acid dissociation constant, and sea salt represents the concentration of the salt that is taken. So putting all this value, we find out that the pH of the solution is 8.58. So after determining the starting and end points of the titration, we now consider pH calculations for intermediate points. So hence, for any calculation, we can find the pH values using the concentration of H plus using this formula. The concentration of H plus is given as Ka into concentration of acid divided by concentration of salt. So for particularly for acetic acid, since we have Ka is equal to 1.75 into 10 to the power minus 5, substituting all the values of this, we obtain that the pH of the first intermediate plot is this. Now again putting the value of the titration curve, we find that the pH is equal to pKa. So overall, when we look into the before and after equivalence point for acetic acid, the curve looks like this is the in figure 3.7. It shows the pH titration curve in B, point 0.5 acetic acid with zero point 0.5 NaOH, whereas in 3.7a we see the pH titration curve for zero point 0.5 HCl with zero point 0.5 NaOH. These is the basic difference when we plot the pH titration curves. We have, particularly when we consider the pH titration curve of zero point 0.5 acetic acid with sodium hydroxide, we find the buffering action of the acetate ion that is not present in the titration curve of a strong acid with a strong base. Now, when we look into the titration curve of a weak acid with strong alkali, that is in figure 7, 3.7b, we come across three stages. The starting point of the titration is less acidic when a strong base is added. Here in this case, it is less acidic. The equivalent point is weakly alkaline in nature. We can see this is the equivalent point, which is weakly alkaline in nature. The middle part of the titration slants more towards the titration of the strong acid, and the titration jump is not great. From 8 to 10 particularly, we see it is not great. The vertical part of the curve is smaller than when a strong acid is titrated. When we look into figure 3.7a, this the slope is more, the difference is large, whereas in figure 3b the slanting is less. Now here in particularly 3.7b, the buffering action of acetate ion plays a greater role. When HCl was titrated with an alkali, so the approximate change so is very less. This difference arises because of the fact that titrating a strong acid with a strong alkali, the concentration of H plus ion decreases because as a combination with OH minus ions to form with water. When we titrate a weak acid with a strong alkali, the H plus ions they not only combine with OH minus ions, but the H plus ion also combine with the acetate ion. As a result of which, the concentration of H plus ion decreases more rapidly at the beginning and the titration curve bends downwards, which is not in the case of a titration of a strong acid with a strong alkali. So when after an effect of the acetate ion, thus it smooths out the titration curve. This is known as the buffering action. The value of H plus in the solution of a weak acid in the presence of its salt is determined by this. We have this formula H plus dissociation constant of acid into concentration of acid by concentration of the salt. So considering all the equations above, we find that pH is equal to pKa, pK of acid. This means that if the concentration of the acid and concentration of the salt, they have close values, they are the quantities are same in the mixture, then the pH of the solution will remain constant even when considerable amounts of acid and alkali are added. Precise this relation has been observed in the case of titration of a weak acid with a strong base at the after the second intermediate point, not at the first. Here, this is the second intermediate point and it remains constant where pH is equal to pK acid. This is an important finding. And next is modified glass electrode and state membrane electrodes. Now we know that glass electrodes are ion sensitive in nature. So this they can also be, particularly they are sensitive to H plus ion. But glass electrodes can be made selective for ions other than H plus, and we need some manufacturing modifications for this. This modification is possible by changing the composition of the glass and the internal solution of the electrode. Mostly aluminium oxide Al2O3 has been added and silicon and changing the internal filling solution from HCl to sodium chloride. Such electrode they become selective to Na plus ion. There is another type of glass electrode where the composition is lithium oxide Al2O3 silica to form a sodium electrode. Sodium electrode has many applications, particularly in measurement of the presence of sodium in water analysis and in biological fluids. For measuring potassium and ammonium ions, glass electrodes have been modified that contain 27% sodium oxide, 4% alumina, and 69% silica. The potassium ammonium electrode is now replaced by other ion selective electrodes, more selective membranes. So it is not only that we can prepare glass electrodes that are sensitive to H plus ions, with greater development, glass sensitive electrodes that are sensitive to Na plus, K plus, and and NH4 plus have also been prepared, and other such sophisticated glass electrodes are being prepared to sense other ions apart from H plus. Now we have solid state membrane electrodes. In solid state membrane electrodes, we used a doped single crystal membrane in the place of a glass membrane. These changes, why this change is important? Because it enables us to design electrodes which have a response to different anions such as F minus, Cl minus, and Ag plus. Now, when a typical example is shown here, this is a solid state electrode. So here in this solid state electrode, similar system to glass electrode internal solution and electrode forms the internal reference. So fluoride ion selective electrodes that consist of lanthanum fluoride LaF3 membrane and an internal AgAgCl reference electrode has been prepared that contains an internal solution of potassium fluoride and potassium chloride. LaF3, the lanthanum fluoride membrane, is highly sensitive and it responds to fluoride ion particularly. So if this electrode is used with a reference saturated calomel electrode, the complete reaction is given by this. So the this is one example of of an electrode that is sensitive to F minus by the use of LaF3. The total potential of the electron is given as E cell is equal to E star minus 0.0591 log of AF minus. So here the E star again it includes all the factors that consists of E AgCl of the E standard calomel electrode, the asymmetric potential, the liquid junction potential, all the all these factors have been represented by the factor E star. The calibration with the known fluoride electrode activity eliminates the need of these constants. As we know from the previous study, the calibration is important for any glass electrode. Similarly, the calibration of fluoride electrode also eliminates the other factors and it displays the exact pH value corresponding to the fluoride concentration. So fluoride electrode has many applications such as determination of fluoride in bone, air, stack gas samples, chromium plating bars, minerals, toothpaste, and other places where fluoride is present. Now, similar to fluoride ion electrode, other electrodes, solid state membrane electrodes, have been developed. Some of the examples have been listed above, such as for a selective ion F minus, LaF3 membrane is used. For Cl minus, AgCl is used. For Br minus, we have AgBr. Similarly, to sense cadmium, CdS, Ag2S is used. To sense Pb2 plus, PbS, Ag2S membrane is used. So this is an indication. This list in table 3.1, it shows the various types of selective ions and the membranes that have been used to sense these ions. Now, based on the principle of ion selective electrodes, gas sensing electrodes have also been developed in the past few years. They are primarily available for the measurement of ammonia, carbon dioxide, and other gases in the atmosphere. This type of electrode, they have a gas permeable membrane and an internal buffer solution. So the pH of the buffer solution, it changes as the gas that is passed through it reacts with it. The change is detected by a combination of the sensor. Then this electrode, it does not require a reference. So this works just with the by the reaction of the gas with the buffer solution and the pH of the solution that is changed as a result of this reaction. So in table 3.2, we have a summary of several typical gas sensing electrodes. Like for the test to sense ammonia, an internal electrolyte of ammonium chloride and the it is taken, and the ion selective electrode is pH, but the pH electrode we have taken, whereas the membrane is PTFE, polytetrafluoroethylene. Now to sense H2S, hydrogen sulfide, the electrolyte chosen is sulfate buffer. So this ion, this electrode, it senses S2 minus, and the membrane that is taken is silicone rubber. Now as you can see, these membranes are all inert in nature, so they just act as the membrane, whereas the internal electrolyte is an important factor which decides the which senses the test ion or the gas when it passes through it. Now there are applications of ion selective electrodes. Ion selective electrodes, they, along with pH sensitive electrodes, are widely used in analytical chemistry and research applications. They are also commercially available electrodes for detection of H plus, F minus, Cl minus, and other ions, and also gases like nitrogen oxide and several carbon dioxide, sulfur dioxide, ammonia, and also other enzymes. pH, in most of the cases, glass membrane electrode is commonly used as the ion selective electrode. pH measurements have many applications like pH metric or electrometric methods. They help in detecting the endpoint of acid base titration. pH metric is an important tool in analytical chemistry for studying the acid base equilibrium, which is controlled by sodium dioxide bicarbonate equilibrium in most. And as has been studied by pH metry to proceed with the use of by monitoring the pH in neutralization of wastewaters. The pH metry is used to evaluate the dose of acid or alkali that needs to be added, and pH metry is very important for the development of biosensors, to develop new sensors for pH sensitive enzymes that is needed in our body, and the study the various reaction mechanisms. However, also there has been flexibility in the configurations available. We have also flow injection analysis of pH metric. Thus pH serves a very important factor in analytical chemistry. So in summary, we can say one of the most common and earliest applications of potentiometry is pH determination. Through development of different types of electrodes and the ion sensitive electrodes, particularly the sensing of inorganic, organic, gaseous, and biological important ions have been possible. However, the flexibility in also in these configurations have also been monitored, and they have also been used in conjugation through a flow injection analysis, which is highly the flow injection analysis is highly essential in biological systems. So this is all about pH metry. For this solution, pH meter, the use of pH meter, the various types of pH electrodes, the glass electrodes, and their apparent applications, common applications. So with this, we complete Unit 3, that is pH metry. So now we'll take a just break of 5 minutes and again continue with Unit 4, that is conductometry. So, start coming to the next unit, that is conductometry. So, as pHmetry is an important unit, this is an important part in electrochemistry. Conductometry also plays a significant role in electrochemistry. It is a very important tool in analytical chemistry. Now, before going for details into conductometry, let us understand what do you mean by an electrolytic conductance. So, first is conduction. Conduction is mostly means when a compound is allowed to flow throughly in an electrolyte lytic solution that contains free ions. So when the free ions, when they come under the influence of an electric field, then the migration of the ions takes place. This phenomena of the decomposition of the solution by electrocurrent, as we know, is called as electrolysis. Now, electrolysis in general implies the breaking of a compound into its solution and the migration of these ions to the respective electrodes in presence of an electric current is called as electrolysis. So, the migration of these ions to the respective electrodes will not occur unless the ions of the electrolyte are free to move. So, an electrolytic conduction is exhibited by the ions by salts in their molten state or in their aqueous solution. So the principle of electrolytic conduction has been shown in figure 4.1. So this figure 4.1 explains the electrolysis of molten sodium chloride between inert electrodes. The entire assembly is known as the electrolytic cell. So the electrons are received from the negative end of the cell battery, as you can see the Na plus ions. So for when electricity is passed through molten sodium chloride, it dissociates into Na plus ions and Cl minus ions. The Na plus ions, when electricity is conducted, when electricity is applied to the circuit, the Na plus ions, that is the cations, they move towards the negative electrode and which is called as the cathode, whereas the Cl minus, that is the anions, they move towards the positive electrode that is called as the anode. So in general, we can say that the cations move to the cathode and the anions they move to the anode. Thus, the mobility of these ions moving towards the respective electrodes plays an important role. The factors that it particularly influence the electrical conductivity, it includes the nature of the electrolyte, the interionic attraction, the solvation, and the viscosity of the solvents. These factors depend on the attraction, that is the solute-solute interaction, the solute-solvent interaction, solvent-solvent, and many other factors. The average kinetic energy of the solute ions increases as the temperature is raised. So, electrolytic conduction is also dependent on the temperature at which the entire process is carried out. So, based on the nature of electrolytic conduction, there are two important classes of compounds called as electrolytes and non-electrolytes. The ionic compounds which furnish ions in solution and also conduct electric current, they are called as electrolytes. Like we have ionic compounds like NaCl and KCl. Certain covalent compounds also conduct electricity but in small quantities like HCl, CH3CO minus, acetic acid, etc. The other remaining substances which do not form ions, they in solution are called as non-electrolytes. That is cane sugar, benzene, CCl4, etc. So sometimes electrolytes are further, they are classified into strong electrolytes and weak electrolytes. Now they can be strong. This has actually, the word strong and weak does not imply their concentration. The strong electrolytes are those compounds which completely ionize in their solution or in molten phase, such as, like example is NaCl, NH4Cl, HCl, HBr, etc. The weak electrolytes are the compounds which ionize only to a certain extent or a very minimum extent. Common examples are acetic acid, HCN, and others. The term that we use, strong electrolytes and weak electrolytes, they are very relative to each other. The behavior of the electrolytes is also dependent on the nature of the solution. Like, for example, NaCl behaves as a strong electrolyte, whereas acetic acid is a weak electrolyte in water. But on the contrary, when we dissolve in ammonia, NaCl and acetic acid, they almost show comparable behavior. So that is why the nature of the electrolyte that is taken into consideration plays a very crucial role. So, next is conductance of solutions. This implies the ease of the flow of electric current through any body. That indicates the conductance of the material. So, in metallic conductors, particularly we know metals are conductors and it is caused by the movement of electrons, which while in an electrolytic solution, it is caused by the ions. The electrolytic conductance represented as G is given as G is equal to I upon R. So 1 by R, where R represents the resistance in ohms. So conductance is the reciprocal of electrical resistance. G is equal to 1 by R and its unit is ohm inverse. Now from Ohm's law, we know that I is equal to E upon R, where E represents the volts in volts and R is in ohms, or I is equal to Eg. Now, since a solution is in a three-dimensional conductor, the exact resistance it will depends on the spacing L and the area of the electrodes. So we can write it considering. Let us consider a electrolytic cell that is shown here. The resistance is directly proportional to R. It is inversely proportional to the area. So R is directly proportional to L by A, which is equal to R is equal to rho into L by A. Rho is the proportionality constant. It is called as resistivity. Formerly, it was called as specific resistance, but now it is called as resistivity. So, it is a characteristic property and its resistance offered by a conductor. So rho is defined as R into A by L. It is defined as the resistance offered by a conductor of unit length and unit area of cross section. So the in SI units, the resistance, the L and A are measured in meters and square meters respectively, and the resistance is offered in omega or ohm that we write. So therefore, the unit of rho is ohm into meters. So formerly, resistivity measurements were made in terms of centimeter cube. However, currently we are using ohm meter. Now substituting the value of R, the total, now the new expression for conductance G is given as G is equal to 1 by R. This is equal to 1 by rho into L by L, A by L. This is kappa into A by L, where kappa is the reciprocal of specific resistance. It is called as specific conductance or conductivity. The unit of kappa is ohm inverse, meter inverse. This quantity may be considered as the conduction of a cubic material of single length unity. However, in SI system, the unit for conductance is Siemens and it has been given the symbol of S. So therefore, the unit of conductance is Siemens meter inverse, that is 1 Siemens is equal to 1 omega inverse. So it may be remembered that Siemens per meter is equal to 1 by 100 Siemens centimeter per centimeter. So, however, customarily, most of the reported units are in millisiemens per meter or microsiemens per meter. So, cell constant. For a given cell, L and A are constant, and the quantity L by A is called as the cell constant K, which is given as K cell is equal to L by A. It should not be confused with kappa. So the cell constant is given by K cell. So kappa is equal to G into K cell. That is, we can write it as conductivity is equal to the conductance into the cell constant. So to obtain the value of cell constant, it is usually not necessary to determine L and A directly. Instead, we measure it by a solution of known conductivity. And for this purpose, KCl solutions have been invariably used because their conductances have been measured with accuracy in known dimension, cellular dimensions. So a given solution of KCl of conductivity kappa dash is placed in the cell and its resistance R dash is measured. The cell constant is then equal to kappa dash r dash. Therefore, the cell constant is given as kappa dash into r dash. That is, kappa dash implies the conductivity of the KCl solution, and this r dash is the resistance offered by the KCl solution. So, conductance is an additive property, that is, in an aqueous solution containing several electrolytes, the total conductance G total is given as summation of G of I plus G of water, whereas G of I indicates the individual elements and G of water is actually negligible in comparison to sigma Gi. So G total is mostly summation of the sigma of Gi. So this is about your conductance and cell constant. Now, with relative to conductance, there is an important term, that is molar conductivity. In order to compare the conductivities of different of electrolytes, a quantity called molar conductivity is frequently used. It is represented by lambda, by the capital lambda and the small m as the subscript. The subscript m, it indicates the molar conductivity. So, and this is given by the relation kappa by C, where C is the concentration of the solution. The molar conductivity is usually expressed, the unit is usually expressed as Siemens meter square per mole or Siemens centimeter square per mole. This is the unit of lambda m. So if the concentration is given in molarity, then the following conversion is given out. C is equal to molarity into 1000. These are some of the common. So for to calculation of lambda m, we need to convert the concentration into molarity followed by the use of the original formula. Now, the variation of conductance with concentration. The conductivity of a ionic solution, it increases with ionic concentration. For strong electrolytes, the increase in conductivity increases with concentration, and the increase is very sharp in nature. However, for weak electrolytes, the increase in conductivity is gradual. However, in both the cases, we see that the increase in conductivity with increase in concentration is because of the increase in the number of ions per unit volume of the solution. Now, for a strong electrolyte which undergoes complete ionization, the increase in conductivity is directly proportional to the concentration of the solution. However, in weak electrolytes, where the increase in specific conductance is not large because the degree of ionization is low, subsequently, the rate of increase of conductivity is not very fast. It increases at a gradual pace. So, in table 4.1, the variation of molar conductivity with different for a number of electrolytes at various concentration has been depicted. You can see the lambda m for KCl, NaCl, HCl, and other for strong electrolytes, and a comparative with weak electrolytes has been provided. It can be observed that the molar conductivity, it increases with decreasing concentration for both weak and strong electrolytes. If we look into this, we find that lambda m also increases when we decrease the concentration for both weak and strong electrolytes. If we plot the molar conductivities of a large number of electrolytes against the square root, we find of their concentration, we find that they fall into two distinct categories. So in the case of strong electrolytes, there is a small increase in molar conductivities with the decrease in concentration. Since these electrolytes, they dissociate completely even in concentrated solution, the number of ions do not change very much with concentration. Therefore, the conductivity also does not vary much, and it is directly related to the number of ions in solution. These minor changes are observed due to interionic interactions. However, for weak electrolytes such as acetic acid and ammonia, the ionization will increase with dilution, and hence the molar conductivity increases with dilution. Thus, conductivity is directly proportional to the degree of dissociation of a weak electrolyte. Now, when from figure 4.2, we see the variation of molar conductivity, that is lambda m or versus concentration square root of concentration. It shows that for KCl, it shows a linear plot, almost a straight line, whereas the weak electrolyte, it approaches a dilution and then has a tangential limit. It is impossible to draw a sharp line of demarcation between the two categories. You see, both behave. So in many cases, sometimes some substances they are known to show intermediate behavior, such as nickel sulfate. Such electrolytes they are called as moderately strong electrolytes. This is the variation of molar conductivity with dilution. Now, the conductance of a solution is also dependent on the number of ions and the speed of the ions, that is, the mobility of the ions in the solution. In case of strong electrolytes, the number of ions is almost remains the same throughout at all dilution, because in a strong electrolyte it undergoes complete ionization, and the variation of equivalent conductance with dilution remains is is therefore due to the change of the speed of the ions. In a concentrated solution, such electrolytes, the interionic attractions they oppositely attract the charged particles. The ions may also form sometimes ion pair type, like which comprises of A plus and B minus. So various all taking at infinite all these factors contribute to the formation of an infinite dilution. As the dilution is increased here, in the case of a diluted, as we increase the dilution, the interionic attraction decreases and the ions they move freely and independently of their coions, and thus they increase the lambda m with dilution. So at infinite dilution, when we dilute the solution infinite times, the ions are much farther apart from each other, the interionic attractions are absent, and each ions it moves independently without its coions. The molar conductivity then approaches a limiting value at this infinite dilution, and it represents the conducting power of 1 mole of electrolyte, so that it completely splits up into the ion. This state is called as lambda infinity, which represents the molar conductance of the electrolyte at infinite dilution. So it can be concluded that in case of weak electrolytes, the increase in molar conductivity with dilution is mainly due to increase in I is mainly due to increase in the number of ions in the solution. Degree of ionization it increases with dilution, and smaller interionic attractions at higher dilutions. So an important relation that can be obtained by extrapolating the curve shown in here in this figure 4.2 is the case of limiting molar conductivity. The limiting value obtained by this extrapolation is called as the limiting molar conductivity at infinite dilution. So observing the linearity, if we observe the linearity of lambda m versus lambda c, Coleridge he suggested an empirical formula, that is lambda m is equal to lambda infinity minus b root c, where b is a constant for the electrolyte and lambda infinity is the molar conductivity of the electrolyte at infinite dilution. So this validity of the equation is valid for electrolytes like HCl and KCl. To obtain the lambda infinity, the graph is extrapolated from c is equal to 0 to get the value of lambda infinity. However, lambda infinity has also been computed from molar conductivities at different ions, and it has been found that lambda infinity is equal to lambda infinity of the cation and lambda plus the lambda infinity of the anion. So the molar conductivity of the ionic species is a measure of the amount of current ions carried by the ions that we have considered. Like for example, we consider the Na plus is compared with half of Mg2 plus, right? So the value is given here. For the cation H plus, the lambda value is given here, and then for the anion, the lambda infinity value is given here. So the size of the cation or the anion, it plays an important role in the mobility of the ion. So this is given, and the next part, that is ionic mobilities and transport number. Now, the next question that comes the value of conductivity is, why should there be a difference between the values of limiting lambda m? The answer is that different ions have different mobilities in solution. The mobility of an ion in any solution is dependent on the size of its hydration sphere. The ionic mobility is defined as the velocity with which an ion it moves under a potential gradient. So if the size is bigger, the size of the hydration sphere is bigger, the mobility of the ion is low. So interlinking all the possibilities, the lambda infinity for a cation and an anion for a cation is given as Z plus U plus F, and for an anion lambda infinity for an anion is equal to Z minus U minus F, where Z plus and Z minus are the valency of the ions that we have taken. U plus and U minus it represent the ionic mobilities, and capital F represent the Faraday constant. Okay, so in the above equation, if one of the two quantities are known, then the other can be calculated. So to particularly find the value of lambda cation at infinity and lambda anion at infinity, we define another quantity that is called as a transport number, or sometimes it is called as a transference number, which is indicated by T plus or T minus depending on the type of the on the nature of the cation or the anion. So this T plus is mostly given as lambda infinity of plus by lambda m, and T minus is lambda infinity of minus by lambda m. The transport number and limiting molar conductivities, they are measurable quantities. Hence, the molar ionic conductivity can be calculated from this equation that is given in 4.414. So from the value of T plus and T minus, we can have an idea about the lambda m. So the limiting molar conductivities for some of the common ions have been given in table 1.4.2 for cations and anions. These values, they are important in predicting the molar conductivity of electrolytes, and further in conductometric titrations. Some of the typical values have been reported here. It is interesting. We see if we look into Li plus ion, because of its larger hydration cell, it has a lower mobility than K plus. So exceptional mobilities have been observed. So right in another case, similar can be attributed to F minus and Br minus. So exceptional mobilities have also been observed for H plus and OH minus. If you look into the mobility of H plus, it is 36.24 into 10 to the power 8, whereas OH minus is 20.58 into 10 to the power 8. So this is because these case charge is transported to through proton jump mechanism, considering the case of H plus ion. So this results due to this proton jump mechanism as depicted here. The result This result is equivalent to the migration of charge from left to right. This conduction mechanism is more like a charge ion movement. Such conduction is particularly possible for peculiarly for water or hydrogen bonded solvents. This is plays, and also it affects the value of the conductometry. Now, effect of other factors on conductivity. Beside concentration, there are some factors which affect the conductivity of the electrolyte solution. The first is effect of temperature and pressure. The conductivity of all electrolytes increases with increasing in temperature. The variation of lambda m at infinity is given by this empirical formula. Lambda infinity is equal to lambda infinity at 25 degrees centigrade into 1 plus x t minus 25, whereas tx is a constant and the t represents the temperature at 20, and t is the temperature of the electrolyte. So the conductivity increases slightly with pressure. As conduct The effect is mainly because is dependent on the viscosity of the medium. Therefore this decreases with an increase in pressure. Consequently, equivalent conductance of the solution will increase with rise in pressure. Next is effect of solvent. In solvents that have very low dielectric constants having small ionizing effect on the electrodes, the electrostatic forces between the oppositely charged, it would be appreciable, and thus the equivalent conductance would have a very small value. However, when the dielectric constants are very high, the conductance of the solution also increases. Now, next factor affecting the lambda m is the viscosity of the medium. The dependence of a conductance on the viscosity of the medium is given by Walden's rule, according to which the equivalent conductance of an electron of an electrolyte is inversely proportional to the viscosity of the medium. That is, the lambda 0 is the equivalent conductance at infinite dilution. It is, and eta 0 is a coefficient of the solvent. So here lambda 0, lambda infinity and eta 0, they are inversely proportional to each other. Okay, these are some of the factors that affect the lambda m, that is the conductivity. Then measurement of electrolytic conductance. For measuring the conductance of a solution, we invariably measure the resistance offered by the solution. For measuring the resistance, so if the this measurement is basically based on the principle of Wheatstone bridge. So therefore, to understand this, first look into the principle of a Wheatstone bridge. From this figure, from figure 4.3, it explains the working of a Wheatstone bridge circuit. Now it is employed to measure the resistance of an electronic conductor. This works on the principle of obtaining balance between two arms with the help of a balance indicator like a galvanometer which is attached to it. Now the Rx that is shown here is the unknown resistor. We don't know the resistance, and R1, R2 are standard resistor, R3 is an adjustable resistor, and G is the galvanometer. So to measure the resistance Rx, here the tapping key, that is K, it is hold, and the bridge is balanced by adjusting R3 to get no deflection in galvanometer. So mostly by using this, we calculate the Rx is calculated in the bridge. The total current is divided into two parts, okay, through R1 and R3. And from this equation, the Rx, the resistance of the Rx is given as R2, R3 by R1. This is by following the basic principles of physics. So once we calculate Rx, R1 and R2, when all are known, the conductance, because since this gives the value of resistance, the conductance will be given as G is equal to R1 by R2, R3. So alternatively, the conductometric cell can be incorporated into operational amplifier control circuit. The amplifier balances the potential of the two inputs. The output potential will be given by this factor, whereas R is the resistance of the conductometric cell and RF indicates the feedback resistor. So with respect to the solution conductance, the equation becomes this: E0 is equal to EI, E0 is the output potential, EI RFG plus 1. So by based on this equation, we can find out the total resistance. This is the principle of a Wheatstone bridge. So now the measurement of conductance in solution is carried out based on this principle. However, certain points that need to be considered is that a direct current would actually polarize the electrodes. Hence, so a suitable conductivity cell is located. Since the cell also acts like a small capacitor, the CB must be connected into bridge. So there are certain factors. This is a conductivity bridge circuit which follows slight modifications from the Wheatstone bridge. So in a conductometer, it is a reciprocal of resistance. Now we know that conductance is the reciprocal of resistance. The inverse of the resistance being conductance and can be directly measured on the conductivity called as conductometer. So this figure 4.6, it shows a typical conductometer that is used for laboratory purposes. These are very inexpensive conductometers that are also commercially available. They come as a line operated unit without any digital readout. So it gives us so what we can do, these are the various types of, this consists of various types of cells that have been designed, like they are made of pyrex glass that is fitted with electrodes of platinum or gold to overcome the imperfections in the current and the other effects. So what happens, these electrodes, they are coated with a finely divided platinum black. This is achieved by electrolyzing chloroplatinic acid in lead acetate. So a magnetic stirrer is used at the and can be placed here. This is a conductivity cell. So for most purposes, a special cell is not required. So with this arrangement, the dipping cell is it is dipped into the liquid so that it electrodes become thoroughly mixed. For checking this, the dip type of cell conductivity is mostly used. In some titrations, an open beaker with fixed electrodes is sufficient. So sometimes we do see interference from atmospheric carbon dioxide, so it has to be done in a closed apparatus. So the procedure is quite simple. The first, the current is supplied to the instrument, then the frequency selector is mostly set to 1000 hertz. The mode selector is set with the help of sensitivity knob. The pointer is roughly set to the highest and lowest sensitivity, say at position like 1. So once the connectivity cell is connected, and then it is with distilled water, the conductivity water that comes with the instrument, the standard KCl solution is taken, the conductivity cell in the solution, and then after the instrument is switched on, the conductance of the KCl solution was first measured. It is removed from the standard KCl solution and it is dipped in the unknown solution in a similar manner. So the K cell is given as conductivity, that is the specific conductance divided by the observed conductance of the standard. So similarly, the conductivity of the unknown solution is defined as kappa u is equal to for K cell into G of the unknown solution. So this is how it is calculated, and in sometimes in automated conductometers it is directly displayed into the system. So, while there are certain precautions, like when the range selector is switched to a new position, it is essential to check the calibration point. So, calibration point is always important to so that it lies between it is set to 1000 hertz. The conductivity cell, it should be kept in distilled water to prevent the drying of the platinum electrodes. As we know, the electrodes is coated with a thinly divided platinum black, so it should always be kept in distilled waters to preventing the drying. In case of fouling the conductivity cell electrode plates, they are cleaned in dilute chromic acid that, and then they are washed with running water followed by rinsing with distilled water. So a proper cleaning of the electrodes is required to prevent its molding and bacterial growth. The applications of conductometry. Now conductometry plays is widely used in it is a highly sensitive instrument, and it is used in an important analytical tool for environmental and other analytical applications. Conductance, since it depends on ionic concentrations, the purity of steam, water, and ionic contents can be checked. Certain metal industries like electroplating baths, and they are monitored by conductance methods. Perhaps the most common actual application of conductimetry has been estimating the purity of distilled water. This is quite an important application of conductometry. Collage, he first introduced this concept of measurement of purity of distilled water by conductometry. In vacuum, he obtained the kappa for distilled water to be 4.3 into 10 to the power minus 8 Siemens per centimeter inverse at 18 degrees centigrade. Now, the traces of an ionic impurity, it increases the conductance measurement appreciably. In ordinary distilled water in equilibrium, it has a conductivity of about 7 into 10 to the power minus 7 Siemens per second. The seawater has a much higher value because of the presence of salts, and that is why conductometric measurements are widely used to check the salinity of water in different oceanographic studies. Now, measuring the conductance of solution also helps in finding the moisture content of cells at various places. Since soil contain varying amount of water, so these salts, water soluble salts, are present in the soil. These salts are usually mostly in the form of sulfates, chlorides, carbonates or bicarbonates, and they contribute to the conductance of the soil. So the soil may be classified as a saline and non-saline depending on the nature and quantity of the salts present. Thus, the conductivity of the saturated salt with water of saline at 25 degrees centigrade must have a conductivity greater than 4 millisiemens per second. So the analysis of salt, the analysis of presence of different types of salts has also been performed by conductometric titrations. And now, based upon the relative change in the conductance resistance of a solution, various methods have been developed for the titration of a strong acid with a strong base, weak acid versus weak base, and many other such combination. Other types of titrations which can be performed conductometrically, it include displacement titrations, such as which employs sodium sulfate versus HCl, or ammonium chloride versus sodium hydroxides, and other such experiments. So redox titrations have also been done by conductometric measurements, such as redox titrations like the titration of Fe2 plus versus KMnO4, which is a very common example of a redox titration. Conductometric titrations are also based upon precipitation or complex formation reactions. However, these are not as useful, those involving neutralization processes. The precipitation and complex formation reactions are as such complicated in nature. So, conductometric titrations has mostly been performed for neutralization and redox reaction. The conductance changes during these titrations are never large, and thus they cannot be captured with precision like those observed with the neutralization reactions. The main advantage of a conductometric endpoint lies in its applicability to very dilute solutions and to solutions that involve relatively very incompleteness. So, for example, when we talk about successful neutralization of phenol, neither a potentiometric titration nor an indicator can be successfully employed to understand the neutralization of phenol, which has a Ka of 10 to the power minus 10. However, in this case, conductometric titration have been successfully employed to understand the neutralization of phenol, and it has depicted accurate and precise results for this process. So direct measurement of conductivity is potential. It is a very sensitive procedure for the determination of parameters like the degree of dissociation of weak electrolyte, dissociation constant, ionic product, solubility product, Kw, and other factors. So, in summary, various parameters, the resistance, conductance, resistivity, kappa equivalent, these have been detailed here. The relationships among these parameters have also been known here. So, we also talked about the various applications of conductome here, how conductometric titrations, it can be used in redox titrations, acid base titrations. So, we have also come across it. So, this is apart from being used in analytical chemistry, conductometric titration have also been used for the determination of other conductances. So with this, the conductometry part comes over. So if there is any question to ask.
No, ma'am.
Okay, thank you.
Thank you, ma'am.